All right. Welcome to a new NAGROM's seminar. Um, it's I'm delighted to introduce the speaker is Youngsoo Choi from Lawrence Livermore National Laboratory. And today, Youngsoo will talk about physics-guided and interpretable data-driven simulations. So at the end of the talk, so we're gonna have some questions, and you can ask anything you want. So Youngsoo, you can go ahead. Thank you.
Thank you. Thank you for the introduction and Treyan and all the organizers of this NAGRAM seminar. It's an honor. Today, I'm going to talk about physics-guided and interpretable data-driven seminars. Well, data-driven simulation. Well, it's a bit early for me here. Pardon me. All right. So why do we want to develop those physical simulation? Data-driven approaches for this physical simulation. There are so many physical simulations which play an important role, but unfortunately, they are computationally expensive depending on the complexity of your model. At Lawrence Livermore National Lab, we have many complex simulations, 3D printing process simulation, 3D shape charts simulation, or the tokamak electrostatic ion scale turbulence simulations, and seismic earthquake simulation, and core collapse simulation. All those are examples of which are computationally very expensive. They can be accelerated using high performance computing. El Capitan here, I'm pointing at right here, that is a first exascale high performance computing we will have. It's not available to the users yet, but it will be available next year in FY25, I believe. However, recent, the big project like the ECP project, exascale computing project, which ended last calendar year, they have nicely demonstrated that it's not enough to just advance the hardware like the high performance computing. They were able to obtain a more than 50 times performance gain, not only with a high performance computing, but also the development of the advanced algorithms. So we can use algorithm to speed these things up. And one of the way is thanks to the advance in machine learning, we can apply black box data-driven neural net type of data-driven approach, which works like you generate tons of simulation data. For these examples, we generated Rich-Meyer mesh curve instability data, two-dimensional simulations, and you can feed those data into neural network and train them. And once the neural network is trained, you can predict the new solutions very fast. As a matter of fact, this particular examples, we were able to obtain a speed up of 100,000 speed up. But unfortunately, it comes with limitations, as you all probably familiar with, because it relying on only data. It requires big data, which of course brings us an issue of first of dimensionality for this particular problems. It is not bad, but even with the two-dimensional data, we had to deal with a 16 gigabyte, which increases the training cost tremendously, because to train the neural network, you have to solve a nonlinear optimization problem. And even after you train the neural network, it is not easily interpretable because of the complexity, internal complexity, how those neurons are connected and all those weights and biases. It's hard to interpret all those individual components contribute to the predictions, right? And many times, a lot of times, their prediction is not structure preserving. You know, for this rich Meyer-Meshkov instability problems, the momentum of the conservation of mass is actually violated, although they look okay in IGO. This is real concern to physicists. And lastly, but not the least importantly, you know, because they only rely on the data, they are not robust for the extrapolation. For as a matter of fact, this is a density predictions. On at the point right outside of the training data regions. As you can see clearly, the density is evaporating, clearly by violating the conservation of mass. So all these limitations caused by this black box data-driven approach, it can be solved by applying physics-guided and interpretable data-driven approach, which I'm going to go over one by one by talking about each issues. But before I do that, I would like to share a principle, three principles we always keep in mind when we develop the physics-guided data-driven approach or reduced order model in our various projects. We always want our reduced order model to be physics-guided, so that we can achieve a structure-preserving predictions, and also we want our model to be interpretable, so that when our model is trained, we want to know how it works. So in order to achieve that, we want our model to be differential equations, and also a lot of times you may not know what differential equations you need to use. So in that case, we try to use the physics discovery algorithm to identify those differential equations to make our model interpretable. And a lot of times, because we are dealing with the high dimensional data, it's hard to fit those high dimensional data into some sort of model. So what we do is in our data-driven model, you compress the data using either linear compression or nonlinear compression. Once the high dimensional data is compressed, now the size of the data is reduced. You can easily fit those data into some sort of model. As I said before, we want that model to be differential equations, and we do that. And when we identify those differential equations, we also associate those different individual differential equations with corresponding parameter points, so that once this reduced order model is trained, we do not never go back to the high fidelity full order model in space. We only want to do all the computations within the reduced space. So we achieve that by associating or using some sort of interpolation technique to relate those parameters into the differential equations that represent the dynamics in the latent space, in the reduced space. And for the prediction phase, whenever you want to predict some solutions for the new parameter point, you interpolate and come up with this differential equation in the reduced space, and you solve that problem. It's easy to solve it because in reduced space, you get the solutions in reduced space and project back to the full space, right? And that's more or less the framework we follow. For some algorithms, we actually don't follow this framework, but many times this is the framework we are following when we develop the reduced models. Actually, the algorithm, as this seminar series indicates, like Galerkin reduced order model, Galerkin projection-based reduced order model. This Galerkin projection-based reduced model throughout my talk, I'm going to lay out the story so that that also falls into this category. And when I talk about this algorithm and introduce many different algorithms in this talk, I'm going back to the phrase, the latent space dynamics identification, in short, LASDI, LASDI. We chose the word terminology identification just to emphasize the focus. We are going to apply all kinds of the technique to identify the differential equations for the latent space trajectory. And those Galerkin projection or Petrov-Galerkin projection based views for the model falls into this category as well. All right, as I promised, let's try to address the issue posed by the black box data-driven approach, which I described in previous slides. Let's take a look at that one by one and try to address that. First issue is requiring big data. And many, well, not many, pretty much all the data-driven approach, you have to generate the data, and where in your parameter space you generate those data is very important. And if you use the physics information when you sample your parameter space and generate the data, that will reduce the number of total training data you need to generate. So just to illustrate that, if you use the uniform sampling in two-dimensional parameter space, and let's say you sample 7 data points for each dimensions, that requires 49 training points. Let's say you need that to achieve the 1% relative error. That implies that if you are going to deal with a 10-dimensional parameter space, then that means 7 to the 10th power, approximately 300 billion data points you need to generate. And that's problematic if those data are coming from computationally expensive physical simulations. But if you use some sort of the knowledge about the problem, you already know some knowledge about your problem, then you can pick you can do the optimal sampling, and if it requires only 10 training points for achieving 1% relative error in 2D, then even though you go to 10-dimensional the parameter space, you only need 100,000 points instead of 300 million points. Well, the 100,000 points could be a lot if you consider that you are relying on the generating, but you're relying on the expensive physical simulations when you generate the data, but still better than 300 million points, right? So how can you do that? Just to illustrate that, let's say you have a two-dimensional parameter space, and you start with a existing you pre-generated the data, like at the corner. If you have a box constraint, constraint bounds type of the parameter space, and since you have data on those 4 corners, you can initiate the training of your data-driven model. In this talk, as I introduced before, we will consider this latent space dynamics identification type of the data-driven model, and you can train those models using those existing data. And once that the training becomes mature, then you can actually use this model to predict the solutions at some testing point in your parameter space, right? And you do that, and you can actually plug those predictions back into the underlying governing equations if you know those governing equations, and compute the residual and try to find out where is the worst points in terms of the residual norm of your predictions at each point. And for this particular illustrations, this point, like with the 9.5 residual known magnitude of the residual, that is the worst point. And pick that point and generate the data there and feed that into the training of your data-driven model, and you go through this iterative procedure back and forth and until your model reaches the desirable accuracy. So very nice. If you apply that, bring the physics into the sampling procedure, you can actually reduce the number of training data and achieve a better accuracy for this particular illustrations. If you use the uniform sampling and in this two-dimensional parameter space, I think it was the physics was the spiral attraction problems. And if you do that, then using the 25, the data, the 5.4% relative error, the maximum relative error occurs. While if you incorporate the physics into the 3D sampling, then even though you use the same number of training data, you achieve a 2% relative error instead of 5.4% relative error, which is a factor of 2 times better performance in terms of accuracy. All right, well, maybe that's the case that you do not know the underlying governing equations, then the previous sampling procedure is not available. Then you gotta use something else to guide your sampling procedure. You can actually use the Gaussian process based sampling. So the steps and procedure will be the same as the physics guided sampling in this setting. But since you do not know the governing equations, you cannot compute the residual of your prediction of your data-driven model. For that case, as I described before, when you parameterize this latent space dynamics, the model, we use some interpolation techniques, and for those interpolation techniques, you can use the Gaussian process, and Gaussian process model is going to give you the uncertainty informations, and we can actually use the uncertainty informations to guide this the sampling procedure. For example, you look at the variations and find out where those maximum variation occurs in your parameter space, and pick that point as a next training point and add that into the data-driven training and back and forth. So this framework nicely, allows you not to rely on the governing equations, right? Because a lot of times you only know the data, you do not know the governing equations. That happens as actually many, many times. So if you do that and apply this greedy sampling and compare the performance with the uniform sampling, you actually achieve a similar performance you would get when you apply the physics guided sampling. So for these particular examples, 1D, 1B plus of the plasma, the benchmark problems, if you use the uncertainty-based sampling procedure using only 17 data points, you can achieve a maximum relative error of 3.8% over for your parameter space. While if you use the 25 data points, even though you use the more data points for the uniform sampling, the maximum error is worse than the uncertainty-based sampling procedure. All right, so that's one way of addressing the issue of the relying on the big data. Let's visit the second issue, which was the interpretability. And to address that issue, as I said, our group tried to bring the differential equations in our data-driven model. And one obvious way or one obvious choice of the differential equations for the latent space dynamics identification is the linear ODE. Actually, if you take that your differential equations to be linear ODE, then this latent space dynamics identification falls into pretty famous and popular data-driven approach, so-called the dynamic mode decomposition (DMD), that was introduced by Peter Schmidt in his seminal point in 2010. And this method is widely used and very well known. It has been used not only as a surrogate model or reducible model, but also it has been used for the control problems and optimization problems in so many applications. And you know, just for those of you who are not familiar with the dynamic mode decomposition, it actually follows the latent space dynamics identification procedure, which I have introduced in the beginning. First, you generate the data, right? And then in DMD, dynamic mode decomposition, you arrange the data so that the first column becomes the first time step solution, and second column is the second time step solution, and last column is last time step solution. Arrange that in a way that U minus matrix is, from first time step solution to second to the last time step solution, and U plus is the second time step solution to the last time step solutions. And you try to find out the linear operator A, which maps the U minus to U plus, basically mapping previous time step to next time step. Actually, if you do the pseudo inverse of U minus, and then you can find an analytical form of the A operator. But if you do that, then you will, relying on the the full order model scales, right? I mean, this number of rows could be depending on the your full order model simulation complexity. It could be million or billion. So you do not actually want to directly pseudo inverse the U minus. But well, more or less they do in DMD. Using the singular value decomposition, take the singular value of U minus, and then apply the pseudo inverse based on those SVD decompositions. Of course, when you apply the SVD, you truncate the left singular matrix and come up with a reduced basis representations, and you apply you obtain by applying the projections on with a this left singular matrix, truncated left singular matrix, you come up with a reduced operator A tilde. And once you get the reduced operator A tilde, you can, since we are dealing with the dynamic problems, you can apply eigen value decompositions and come up with a analytical solutions for the latent space, and you project back to the full space. So basically, you apply compressions and identify the linear ordinary differential equation for the latent space, and then predict back, projecting back to the full space, and you achieve the prediction. So it follows more or less the latent space dynamics identification procedure. And as you can see, and this is a only data driven, so you don't need to know anything about the the physics or the governing equations, and it was easy to apply many different applications. That's beauty of a non-intrusive method. So as a demonstration, if you apply this DMD to 3D printing process, which was one of the simulations I have shown in the beginning of my talk today, it takes a lot of times. 3D printing is really having a lot of applications and widely used and revolutionized the manufacturing sector about 10 years also, and still widely used in many different industry. But in order to understand the physical property of what's really happening while the 3D printing process is being done, we have to come up with a very complex and delicate and multi-scale and multi the physics, the computational model. You have to build those computational model, and because of the complexity, that the simulation becomes really, really expensive. Because of that, the reduced score model is definitely need to come in and accelerate them with high accuracy. So the DMD could be one tool to achieve that. So this simple 3D printing process simulation model, it takes just 1 hour for one fold simulation, which is not bad with a 25,000 degrees of freedom. If you apply the DMD, dynamic mode decompositions, using 20% of the basis truncations in your SVD, you can achieve a 2,000 speedups already with a 0.1% maximum relative error, which not bad. But if you want to achieve a larger speed up, then this DMD, just like the projection-based reduced model, the accuracy can be tunable. You can truncate the basis further and achieve a 8,500 speed up instead of 2,000 speed up, and of course by sacrificing some accuracy, but not much, like 0.1% to 0.5% relative error. Okay, so linear ordinary differential equations was nice simplest form of the ordinary differential equation, which can be used for the latent space dynamics identification, but you do not have to always rely on the linear ordinary differential equation. A lot of times your latent space dynamics data, maybe your linear ODE is not a good fit for the data you have. If that is the case, then you can actually apply this the regression technique, so-called the SIND, sparse identification of nonlinear dynamics, which was developed and popularized by Brunton and Proctor and Nathan Foots from the University of Washington. And what they have, developed in their algorithm in SIND framework, that actually allows the users to provide the nonlinear function. Well, it doesn't have to be nonlinear. It could be any functions, any right-hand side functions on your ordinary differential equations, and use those nonlinear functions as a library. And what this regression technique does is fit whatever the latent space dynamics data you have, you feed that into your ordinary differential equations with those user-provided nonlinear function, a set of nonlinear functions, and the regression techniques is going to give you the coefficient in front of those each nonlinear functions in this ODE form, and by solving a least square type of problems. And once you do that, the coefficient is identified, and of course we are going to associate that coefficient with the specific parameter points. And if you solve that and apply that to, for example, 1D, 1B plus of equations, we get like thousands of speed ups, and with a 5%, 4% relative error, which is pretty good. But this comes with some limitations because of simply the fact that we are using this strong form of the ordinary differential equations because of this different derivative terms on the left with respect to time for the latent space dynamics. If you have a noise data, then this derivative terms will be corrupted, and because of that, it's turns out that this strong SIND form is not robust for noise data. As a matter of fact, if you apply like just 10% white noise everywhere in your data and apply this latent space dynamics identification using this strong form of the SIND, although it achieves a 5,680 speed ups in average, your accuracy is not that good. 40% relative error, and as you can see, it's blurred. It's clearly makes sense because that's the data you're gonna see, and this data-driven approach is not going to do better than this, and especially because your the model is a strong form, right? The strong form of the differential equations. So in order to address that, um, we came up with this framework called the weak velocity, weak latent space dynamics identification, where instead of the strong form is used, you actually use the integral form, like the weak form, by applying the test functions in your time domains, compactly supported, and then you apply the integration by parts and move those derivative terms in your left hand side to the test function. Of course, the test function, of course, when we apply that, we know the analytical form of the derivative of the test function, so there is no problem of computing that, and so you don't have to worry about approximating the time derivative of the noise data, which is to use the noise data. And on top of that, because we have an integral form, integral gives us a effect of natural filtering, effect on the noise data. So it's those irregular noise data becomes smoothed out and works out very nicely. So if you apply actually this weak form of the SIMD in weak velocity, and even though you have a noise data, you can achieve a not only the great speed up like 6,816 speed up, but also like more than 6 times reduction in error, achieving like the relative error of 5.6% relative error. And in IBOR reference the clean data and the prediction by this weak velocity is almost identical. Pretty nice. Okay, let's move on to the next issue. How can we bring structure preserving predictions, like the satisfying the conservation of loads or some other physical properties? Now here familiar topics to you guys, like the projection-based reduced model can be used to bring the physics into the data-driven model. And in the framework of from the perspective of the latent space dynamics identification, this actually follows that procedure, like the compression and identification of the latent space dynamics, and also the compression to do the predictions. What does projection-based reduced model does, if you think about it, you actually use the underlying physics to derive the differential equations for latent space dynamics. I probably don't need to go over this slide because this seminar is assuming that the audience is experts in projection-based reduced model, but in case, as you all know, it starts with the governing equations and you introduce some solution representation. A lot of times we use the linear subspace solution representation with a lower rank, and you plug that back into the governing equations, you reduce the number of unknowns. But in order to reduce the number of equations as well, you can, for example, apply the Galerkin projections. And if you do that, at the end, what you get is the ordinary differential equations. And by constructions, that is derived by starting from the governing equations, and we just reduce the dimensionality both in test and trial space. And that's how we get the ordinary differential equations, right? And this the solution approximations involves the compression techniques, and these Galerkin projections involves lead to these identifications. And what do we do to predict the new solutions? We actually solve this ordinary differential equations in reduced space for the for example, by applying your favorite time integrator, such as the backward Euler or Longitudinal, whatever the time integrator is, you apply that and get the solution in latent space and predict the solutions in full space. But as you all know, for the nonlinear problems, it scales with the full order model, so you have to apply the hyperreductions, and that there are various different types of hyperreduction, DIM and GNAD, and the gap PPOD types of method, and or E2P, there or ECSW. There are many different types of the hyperreduction, which basically try to reduce the complexity of the nonlinear terms. But recently, we have come up with a new hyperreduction technique in order to improve the DIM or the gap PPOD types of the method by maximizing the column orthogonality and the determinant in order to improve the stability, the behavior of the classical DIM approach. And if you use this criteria and select the points using this SOPT algorithm, then you will actually get better the accuracy when you sample smaller number of the points in your nonlinear the space, as you can see from this the graph, which is actually practical reasons, right? I mean, when you sample small, you want to achieve better accuracy, which can be achieved by this SOPT hyperreduction. So you're welcome to check out this publications. I think it's very, very close to publications. We are at the last stage of the revision and going back and forth between the journal and the addressing the comments, etc. So I think it's close to the publication in CISC, but it is available in archive, so you can check that out. So if you apply this projection-based reduced model, and one of the important the algorithms we deal with in Lawrence Livermore National Lab is a Lagrangian hydrodynamics. And so when you apply this projection-based reduced model for different types of Lagrangian hydrodynamics, the problems like the Rayleigh-Taylor instability, Siddle-Blast and Taylor-Green and triple point problem, of course, you get very tunable the accuracy by changing the basis, and so that make sure like the conservation of momentum, for example, conservation of momentum is preserved. And not only that, like this symmetry in 3D, this problem of the shock shape, which is important to preserve, it is preserved by this projection-based reduced model, which is hard to achieve using the black box data-driven approach, like the neural net type of approach. And recently, we have also developed a super energy conserving projection-based reduced model using also hyperreductions from the perspective of the Lagrangian hydrodynamics, and we achieve that by construction. So we manipulate our basis and introduce some auxiliary basis like 111 unit basis, and also analyze rest of them and embed it into the the energy conserving the constraints, and then we achieve actually the machine precision, the energy the conservations. These two lines is like you can compare without those super energy conserving the method, and with the super energy conserving methods, these are the precision of the energy conservation or violations. You get like close to the machine precision. So we are actually working on the preprints, and once that is available, well, there's a technical report available, but not much details in this technical report. But please stay tuned when that preprint is available. We are expecting to make it available pretty soon. Okay, I guess I have about 10 more minutes, so I can go over maybe one or two more topics. Another topics I would like to introduce is component-wise reduced model. When you deal with a data-driven approach, as the problem becomes complex and complicated, your simulation data size increasing from million to like a billion, or uh, you know, generating terabytes of the data. And when you do that, it's hard to, train. It's even hard to train, and because you have to deal with a large scale the problems. So if you have that kind of issues, then this component-wise reduced model is a way to go. You know, the it's the familiar the term to you guys. Some of you will be like the reduced basis elements method. You know, introduced by the Petra, Tony Petra's group, and along that same lines. That's what I mean by the component-wise use model, where when you have some repeated domain, just like the porous media simulations, as you can see from these two pictures, you know, those repeated, the structure can be identified by these reference components, like by changing the shape of the pore from circle, triangle, star, and rectangle, or sometimes you don't have any pore. And identify those reference components, and the component-wise reduced model, what it does is you actually train the reduced model or reduced basis on this smaller scale by connecting together either pairwise or quadrant wise, and consider many different combinations of your reference components, and actually apply your the boundary condition and initial conditions, and actually solve your underlying physics. For this examples, we are solving the Stokes equations, and when you solve these Stokes equations with the parameterized boundary conditions, you can generate tons of data, because you are dealing with a smaller scale the problems, right? And use that data to train a component to reduce to the model, and you assemble them together. And here we use the discontinuous Galerkin framework in order to allow the discontinuity between the interface when you assemble those reference components together. But at the end, by the regularization types or the penalty types of the constraints, you can enforce the continuity. That's how we assemble and ensure the continuity between the interfaces. And if you do that and actually solve this much larger scale problems by assembling those component reduced model with the different types of boundary conditions, you actually achieve a speed up of close to 1,000. This red line is when you solve that porous media problems in monolithic finite element method, and the blue line is the solving time achieved by the component reduced model. And well, there's a tendency that if you increase the problem size by introducing more components and increase the problem size, the relative error tends to decrease. But as you probably all know, like you can fine-tune those accuracy by increasing the basis size for each individual component. So this kind of method is possible. All right, maybe the last topic I'm going to talk about today is the nonlinear manifold reduced model. Thanks to Kevin Carberg and Dr. Jin for their seminal paper on introduction of this nonlinear manifold projection-based reduced model, where they use the the convolutional neural network and bring that into the projection-based reduced model, the framework. Since then, a lot of attentions and many research, not only from our research group, but many Europeans and other the research group, it has been looked into this nonlinear manifold reduced model, the framework, and there it is nice because it actually overcome the bottleneck the linear subspace projection based reduced model had. As you all know, like the linear subspace reduced model for the problems with the Kolmogorov with decaying slowly, it is not possible to come up with a compact solution representation in linear fashions because your data is basically linearly independent. For these simple examples where the advection dominated, the shock is moving from one part of the domain to the rest of the part. It is hard to achieve a low rank solution representations and achieve a good accuracy. For these particular examples, the maximum relative error was 34.4%. So the nonlinear manifold reduced model, the framework originally introduced by Kevin Carberg and the Jinli, nicely solved this problem by bringing this neural net type of representation into the solution representation, because the nonlinear representation has a higher expressibility than the linear subspace. So even though your problem is advection dominated, you can achieve a low rank, like if you use even though you use the same low rank of 5, tremendous improvement in your relative error is achieved, like less than 1% relative error is achieved. And hyperreduction becomes more important. So our group has came up with this hyperreduction techniques for this nonlinear manifold reduced model and achieve a speed of 11.6. And our group has chosen intentionally used some specific type of the neural net architecture because when you do the hyperreductions, you have to choose the collocation points, and if you have a deep deep neural network architecture, then those connected nodes in the hidden layers becomes increasing and increasing. You do not get much of the computational gain. So that's why our group used a shallow neural network and sparsify the connection so that even after the collocation points, point selections, the hidden nodes in hidden layers are not much. The computational, the complexity is associated. That's how we basically achieve the hyperreduction by applying the masking approach and then building a self net based on what hidden nodes are chosen. But recently, many other groups come up with a different types of the hyperreduction technique. Instead of doing the masking and subnet approach, they use the second decoder, like the second neural network, using the fully connected neural network, and just train the neural network on the latent space dimension to the collocation points only, and nicely introduce and allows not only the shallow neural network in original autoencoder, but also utilize the whatever the architecture you use, like the convolutional neural network. It could be deep neural network, and that kind of the hyperreduction is also possible. So it's good to see that those other types of hyper-reduced to nonlinear hyper-reduced model is available. So, but if you talk about the nonlinear manifold-reduced model, because you have to train the autoencoder, again, as the data size increases, it's problematic because you have to solve a nonlinear optimization problem, whose cost is exponentially increasing as the data size increases. So one way of addressing that issue is bring the physics and bringing the concept of the domain decomposition to where you divide your computational domain into the several subdomains, and you build a nonlinear manifold reduced model for each subdomain, so that the training of the nonlinear manifold reduced model becomes somewhat relieved, because you don't have to train the nonlinear manifold reduced model on the large scale problem. But again, you have to find out how to assemble them, because now your each representation is nonlinear manifold, not the linear subspace representation, which could be the cumbersome to assemble together. And here we use we achieve that assembly of those local component nonlinear manifold reduced model by formulating the objective optimization functions, by minimizing the individual local residual, the sum of the local residual, and then enforcing the continuity in the explicit constraints. And we solve this the objective optimization problem by using the inexact Lagrange and Newton SQP solver. If you do that, then as a demonstration, you can achieve a quite nice online speed ups. And for this one, the impact is not as much as high as for the time dependent problem, because we have demonstrated only the steady problems. For this particular problems, because it's a steady, for linear subspace reduced model, if you increase the basis size much enough, then you will you get close to this relative error you would achieve using the nonlinear manifold reduced model, and achieve a similar online speed up. But this itself gives you alternative to the linear subspace reduced model. But this domain decomposition nonlinear manifold reduced model will shine and give you much more benefits for the time-dependent problems, which we are currently working on, and would like to show later in later seminar on those results when it is available. But for the first step, this is what we have, and this is promising results for the introducing the nonlinear manifold reduced model in domain decomposition setting. All right, let me conclude my talk with some summary and conclusions. I have identified 4 different issues of the black box data-driven approach, and we looked at those issues one by one in order to address and solve those issues. I have introduced the latent space dynamics identification methods, and try to bring the physics into the sampling procedure in order to address the issue of relying on the big data of the black box approach. That way you can reduce the number of the data. And also, if you do not know the governing equations, then you can use the uncertainty informations. And in order to improve the interpretability, we try to bring the differential equations in our data-driven model. One obvious way is using the linear ordinary differential equations. If you do that, then it falls into the dynamic mode decompositions. And also, when you have the noise data, then in order to deal with those noise data in robust fashions, we also introduced the weak formulation of the velocity latent space dynamics identifications. And to bring the physics into the data-driven model, we also introduced the projection-based reduced models. And to overcome the issues of the linear subspace reduced model for the direction dominated problems, we introduced the nonlinear not just the nonlinear, but the hyper-reduced nonlinear manifold-reduced models, and also to resolve the issues of the training of the autoencoder, like the neural net type of social representations. We have introduced the domain decomposition, the nonlinear manifold-reduced model. All right, with that, I hope this talk was useful and informative. And if you have any questions, please let me know. Thank you for listening.
Very nice. Thank you. Thank you, Youngsoo. Very nice talk. Very comprehensive and lots of ideas and strategies. Trying to tackle difficult problems. Thank you. And I really like the connection you tried to make with the Galerkin projection that you stored the models. I really appreciate that. That was very much in the spirit of this seminar. Thank you. Excellent.
Good.
So I do have a couple of questions, but maybe if somebody else wants to start, please raise your hand or just unmute yourself and ask questions. And right now I cannot see any raised hand. So I'm gonna start. So what I really like, so on slide 22, but even on the second to last slide 22, you talked about the weak latent space dynamic identification, which I think is a very nice idea. This is your work with David Boards. And so what I think it's impressive. So basically you're showing, right, this one. So you're showing that if you, for example, if you use Cindy, then and with 10% noise in the input data, you get bad results. But if you use the weak LASDI, then this fixes the problem. And I was wondering if you kind of said this. So is it the integral formulation in the weak LASDI? Is that what? Last day, I'm sorry, weak last day. So what makes it robust with respect to noise? Is it the integral? I thought that's what you said, but I want to make sure.
Yeah, integral is two factors. Like the integral is natural, the smoothing operator. So that helps. But not only that, like the integration by parts, you can actually move this derivative terms to the test functions. So I mean, we know everything about the derivative of the test function.
Right.
We can design that.
I see.
So that you don't have to, take the approximated derivative using the noise data. So that allows to avoid that. So those two factors actually helps.
I see.
So noise data, yeah.
So thank you, Youngsoo. But you see, what this tells me is this. I mean, both of them, integration by parts and the integral formulation. So these are essential components of the Galerkin framework. So to me, this kind of sounds like whatever you have, if you put it in a Galerkin framework, that's gonna make it more robust with respect to noise in the data, which is what I expected, but that you guys have like natural proof for that.
Well, yeah. Well, I think that's a very nice intuition, and I do think that intuition is correct. Although we haven't demonstrated that and applied that. Here, this is a way of addressing the noise data using non-intrusive approach, like the Galerkin projections and Petrov Galerkin projection is intrusive approach. So yeah. Not there's no single the surrogate modeling or reduced to the modeling which will solve every types of challenges we are encountering, right? So
that's right.
Having these algorithms, different spectrum of algorithms, make it available to anyone. That's I guess our contribution.
Beautiful. That's very nice and very honest and very nicely said. I completely agree with your stuff. Thank you, Youngsoo. Any other questions for Youngsoo? I don't see too much. I mean, I have a lot of questions and I will ask you offline. Okay. So for sure. So, but let me ask you something maybe more general.
Mhm.
And as you said, Youngster, so you have a suite of approaches and strategies. And I was wondering whether you have I don't know. So what is the next? What is next? What's your what do you what do you want
Yeah,
to
so
achieve? Right.
right. Well, that's I I have to answer the questions um, from the perspective that from the fact that I am working in the national lab, and the national lab has a um, particular characteristics when you actually do the research. Um, we deals with a large scale problem, a pretty complex problem, like these days, like um, quantum molecular dynamics or the fusion is really hot topic. And because of the global warming, like the carbon capture, like coming up with a innovative the techniques for the carbon captures, liquidations, and those individual applications giving us like a lot of headache, because you have to introduce complex physics, and that naturally giving us a formulation of multi-scale and multi-physics and multi-phase and real headache. And but those headache actually is a great opportunity for us, our reduced model people. That means there are a lot of rooms we can contribute. And and yes, I mean, these days, those pressing applications is trying out for us to come up with a efficient data-driven, reduced to the model, and that's what we are trying to do. And I don't think, um, I mean, although I'm leading the reduced model groups at the Lawrence Livermore National Lab, we cannot do it by ourselves. We need you and collaborate with us and working with us and to solve those problems together. And the nature of those problems is, as I said, it's really, really large scale. So that's why we are looking at this domain decomposition type of reduced model, and bottom of approach, like the reduced basis element or component wise reduced model. And also, to address those abstraction dominated the problems, we are looking into this nonlinear manifold reduced model techniques. And yes, I mean, there are so many directions and works we can accomplish and contribute to those applications, but we should do that together. We cannot do it um, ourselves. So the future directions, well, just to answer your question, um, there are many directions, and we need you. Oh, you're muted. Oh, yeah.
So I'm sorry. So I said that's good because we need you too. So it's like a mutual need. We need these problems. I really think that you're saying that these are tough problems, but we need those. I think it's very good the national labs come up with, these practical problems because
Mm,
that's what should drive the field, not
mm,
academic test problems like the Poisson equation or the heat equation. I mean, real problems, as you know. So
right.
anyway, so I think that this is a very good business opportunity. I like that. I like what I hear. Very good. Okay. Any other? You're right. I mean, these are impressive applications. Any other questions for Youngsu? No. Well, if not, so I'm sure that Youngsu, if you shoot him an email, so the email address was on the first slide, I believe. So I'm sure that it can answer, if possible, can answer your questions. And if just want to thank you again, Youngsu. I mean, I really enjoyed this presentation. Thank you again.
Well, thank
Thank you.
you. Thank you. I enjoyed it a lot. Okay. Bye,
See ya.
Trayan. Bye.
Bye bye.